Okay, so let's now talk about something I briefly mentioned in the last video, and that is collisions. It's very important to understand how collisions work in Houdini. And notice that I called this video DOP collisions, not pop collisions, because what we learn here is important and true for all other simulations, with the exception of RBD, but this will play a role in this video. So when we play this, as you've seen, sometimes our collision looks weird and doesn't seem to really use the geometry that comes in. And that is actually true. In the static object, there is a checkbox called display geometry, and this is an indicator that there's something going on under the hood. And we can turn this off, and then you can even see better that the collision seems to happen inside of that object. Probably what we have to click on is collisions, and here it becomes interesting. So we have two different tabs here, and this is already the first important thing to understand and really confusing. So we have RBD solver and bullet data. Now, you might ask which one is the right one, because we're in pops, right? So we neither use RBD nor bullet. And the funny thing is actually, bullet is what is used nowadays for RBD. So it's a library that is used to simulate rigid body dynamics. We will talk about this, of course, with RBDs. But in the RBDs chapter, we will learn that RBDs actually is bullet. Now, the funny thing is, that's why there is a RBD solver, because before there was bullet, everything was used with the RBD solver or with the RBD-like collisions. But just remember, and this is so confusing, the RBD solver tab is used for everything except RBD, because in RBD, we use bullet now. And this is actually the explanation for the naming, which is very confusing. So RBD solver is what we need. If in doubt, always think it's the RBD solver. And the next thing is you have two options for the collision, volume and surface. And currently the collision detection uses the solver default. And here's where I have to pass. I have no idea what the default is, weirdly enough. Usually it's always volume. So what I do is I completely ignore the solver default, because I never can be sure what it is. So I always make sure I choose what I need. And it's almost always the volume collisions. And this, now nothing happens, because you should make this visible with a collision guide. And now if I turn this on, you can see this is what's actually used for collisions. And you can see this is pretty weird. Now we'll talk about the other one, the surface collision, in a second. Sometimes you need that, but by default you should always go with a volume collision. Now volume collision should remind you of something. Yes, SDFs. So if you can't remember what an SDF is, then please watch the video about SDF, just search for it, it's in the basics. And this, what we see here, is actually an SDF. The blue thing. It's just a representation, not a good representation, but a representation of an internal SDF. And what is important is the resolution of your SDF. Since it's a volume, it has a certain resolution or a number of voxels that is used to represent the geometry for collisions. And this is the uniform divisions. Currently, this whole thing is set to max axes, so it looks for the longest axis when you create a bounding box around the object and divides it into 30 elements. Very often that's too little, and you can see that here actually both objects are represented in a volume. And if I dial this up, you will be able to see, and it doesn't work right now because you have to always rewind to the first frame, otherwise you don't see it. Let's go back to 30, and here you can see if I dial it up now, let's go closer, you can see how the resolution of that blue thing here is increasing. So try to always increase it to a point where it's not obviously broken. So let's try 70, for example. At the same time, be careful not to go too high, because it can be pretty overwhelming for the simulation if it has to calculate too many voxel for the collision. So don't put this on 1000 and then expect your simulation to run in any way efficient. This actually just killed my machine. So be really careful with those numbers. So that just literally killed Houdini for me, so I had to restart. So be really careful with this number. So I set it to 70, and this is much better. And if I go out now and look at the result, you can see, like we saw before, that the quality is much higher. But you could still say, well, it's not good enough, because here there is still something off. So let's go back in and increase the number further, maybe to 200. And let's rewind so that actually does it. And you should be able to see that the resolution of the collision object now increased. And there you go. Now this problem is gone as well. So it's important to keep track of your internal collision representation. Now the rule is whenever you have a three-dimensional object, which most of the cases you actually have, you should go with the volume collisions. And I think most of the time that is the solver default, but just to be safe, set it to volume collisions and then turn your collision guide under volume on. But there are cases where this is not possible. For example, when you have flat surfaces that you collide with. So for example, instead of having those two boxes here, I will do the same with two flat grids. And I will just replace them. And now what will happen is that the points just fall through. Why is that? Because currently they're still read in via the static object, but we have turned on our collision guide and we see the volume representation of those flat planes, and you can see it doesn't work. Of course, you can't create a volume out of a perfectly thin object. So in this case, you should switch it to use surface collisions, and then you can turn on the visibility for that as well. And if I run this now again, then you can see it's pretty slow all of a sudden. So surface collisions are slower, but also you can see at least that we have a collision that works. For flat objects, you have to switch it to surface collision. Now, as you can see, for flat surfaces, you need surface collisions, otherwise it wouldn't work. But when you have 3D objects, I used to say that SDF is the best option. And I changed my mind about this in the last couple of years after doing some research and some projects. And I actually think now that it's actually quite viable to use surface collisions for 3D objects as well. Because when you have very fast points, then SDF is often the better solution because collisions are recognized easier. But when it's all about precision, so you want points to really move along the surface of a geometry very accurately, for example, because your camera is pretty close, then surface collisions can actually be often the better solution, even though they are slightly slower. So nowadays, I actually think I would encourage you to try both depending on your case and see what works best for you. And there is not a clear winner. It's always a matter of what problem you're trying to solve. So I would say for 3D objects, try both, and we will actually see some examples later on where this makes sense. Okay, so I decided instead of just saying try it out yourself, I will give you a couple of examples where we compare the two approaches. So we start with a complex geometry with a lot of detail in it. And here the SDF should be faster. So it's just, a couple of points falling down, nothing special. And the SDF calculation only takes 3 seconds for, I think it was 100 frames or something like that. And the surface version takes 30 seconds, so 10 times more. So in a case like that, where you have complex geometry with a lot of detail, then the surface collision will be much slower because basically the calculation has to test against all these points that we see here. So in a case like that, SDF is better. But on the other hand, sometimes, like we saw, we have the problem of thin geometry, and this isn't even too thin. But here, while the SDF versions, and I have basically an SDF with a high resolution and a lower resolution, and I have a surface solution. And the surface solution is kind of in the middle, speed-wise. So the surface solution takes 6 seconds. The SDF with 200 voxels in one edge, on the longest edge, which is a lot, takes 8.2 seconds, and the normal SDF with, I think it was 50 or something, only takes 1.6 seconds. So it's the fastest. But of course, what you can see here, both versions of the SDF, even the one with a high resolution, is broken. And honestly, I couldn't make this work. The only solution here would be to make the whole thing thicker. But if for some reason I can't do that, then a surface collision is the only possible solution. So it's not always only about speed, it's also about, okay, what works in the first place. Now, one small thing to add to this, we will talk about this later, is when you use the surface collision type, then if you look closely, and let's switch to the side view with space 3, you can see there's actually a gap between the points and the geometry. That comes from the fact that the surface collision needs a certain size of the points, and that, as we know, means it uses the p-scale attribute. Now, usually you don't have a p-scale attribute, so it will take the default setting, which is what we see here. But if you want to lower that gap, just make sure you create a p-scale on the source geometry, our sphere here, so that this attribute will be inherited by the particles. And here I set it to 001, and that will result in a smaller gap, if I rewind, between, as we can see here, between the points and the geometry. So keep that in mind when using the surface collision type. It takes the p-scale into account, and of course that means you can never set it to 0. There will always be a very slight gap, but this gap depends on your camera angle. So from this angle, the default actually was already fine because nobody could see the difference. Okay, so keeping track of your collision setups in the DOP network is very important. Let's go back to the volume representation. And by the way, I want to quickly show you that sometimes you can, currently I switched it, but the volume collision guide is still on. And let's quickly turn it back on so I can turn the collision guide off, and then the surface collision, there you go. So we can, I just wanted to show you that you can represent the boxes as surfaces as well. So one last thing I want to let you know, that you don't actually have to rely on the SDF that the static object calculates for you. There are certain cases, and more senior effects studies do that. They don't actually rely on the automatic SDFs, so to say, but they create their own SDFs. And we know how to do that. For example, we could do that with a VDB from polygons. And we use a distance VDB, which currently is called surface. It doesn't actually matter what the name is, but I usually call it SDF because it's shorter and it's easy to understand, but it doesn't really matter. And here you can see it's the same logic, just with the voxel size, as we've seen before. And the idea is that you create this outside. When you have a very complicated object, generating the SDF can take a while. And sometimes it can even make sense to cache this out and save it for later instead of having to recreate it every single time. That's one of the reasons why you might want to do this. If you want to create your own SDF yourself, then just make sure that your static object actually understands that, because otherwise it will still create an SDF from an SDF basically. And you can tell that it does that by, if we lower the uniform divisions again, maybe to 28, you can see it still does its thing and kind of ignores the resolution from outside, but you can switch it to volume sample. And that just means instead of analyzing, the shape or whatever, just understand, oh, from outside comes already an SDF, just use that. And then in this case, the uniform divisions don't matter anymore because it just takes the resolution that comes in. So you can see if I dial this back and forth, nothing happens because that is now the SDF that comes from outside. And again, to do that, you have to switch your static object to volume sample. But this is a more advanced technique. There are certain cases where this is helpful, but most of the time, at least for a beginner, you're totally fine with using the ray intersect, which is kind of the automatic way of doing it. And then just make sure that you have a resolution that is high enough for your geometry. Okay, so a very important thing, play around with this. You have to understand this for everything in Houdini with very few exceptions. So make sure you get used to it for everything we do from now on. All right, thanks very much and see you later. Cheers.